Hello, everyone. It's an honor to be invited to speak in EAI CloudCamp 2021. I'm Hogg, a postgraduate from Nanjing University of Science and Technology from China. The topic of my paper is KPG4Rec, Knowledge Property Aware Graph for Recommender Systems. Part 1 is the introduction. Collaborative filtering-based models have powerful ability to use the interaction of users and items for recommendation. However, many existing collaborative filtering-based approaches suffer from problems such as sparsity, cold start problem. Apart from this, they can only grasp the single relationship between users or items. To deal with these limitations, researchers incorporate set information into recommendation system. During many cases of set information, knowledge graph connects the most abundant semantic information. Inspired by the widely used knowledge graph, we propose KPG4Rec, which integrates multiple property relationships of items for personalized recommendation. Part 2 is the overview. Knowledge graph connects the most abundant semantic information and fruitful facts. Over the past years, several typical knowledge graphs have been constructed. They aim to describe all kinds of items and their relationship in the real world. A classical knowledge graph is a kind of directed heterogeneous graph as shown in the picture. It consists of massive triples, and these triples are represented as HRT, which denotes the head relation and tail entity. HRT. Node vector generates sequence of nodes by simulating random walks on a given graph, and then these sequences are fed into a neural language model, such as O2 vector, to learn the embedding vectors. By introducing P and Q, the two vector can control the strategy of random walk, that is DFS or BFS. The LSH mechanism is described as follows. After passing two adjacent data points in the original data space through the same hash functions, the possibility that the two data points are still adjacent in the new data space is high. We give a formulation of the recommendation problem in this paper. The matrix of user item interaction is defined as Y. If a user UI has an implicit interaction with an item VJ before, such as behaviors of browsing or clicking, then Vij equals to 1, otherwise 0. In addition to Y, a knowledge graph is also available. With different properties extracted from knowledge graph, property-aware graphs of the corresponding property can be constructed. The framework of KPG4Rec is illustrated in the picture. Given the above information, the goal of our model is to predict whether a user will interact with an item which he or her has never noticed before. It takes one recommended user UI and one candidate item VC as input, and output is the probability score that UI will click VC. Part 3 is the methodology. In order to get the semantic information of an item, we utilize knowledge graph as the set information to assist our recommendation task. Knowledge graph usually connects fruitful facts and connections among entities. The The semantic properties of an entity can be queried through its corresponding HRT triples, where R refers to the relationship of property which we need. An item in recommendation system usually has a matched entity in knowledge graph, thus the semantic information of the item is equal to its mapped entity. They can be extracted as the supplementary of our model. Apart from knowledge graph, we can also construct the user item interaction graph from the interaction matrix Y. You can see in the left part. In this work, semantic information is integrated into user item interaction graphs by adding relationships among items. We can extract these relationships from knowledge graph by simplifying pair of triples. Intuitively, two items could be linked up directly in the graph through their common ground. See in the mid part. For instance, two nodes representing movies will be connected if they have the same director. By linking up all items with the common ground in knowledge graph, a brand new kind of graph named property-aware graph is generated. In addition, the original directed graph is converted to an undirected form for simplify. In KPG4Rec, we construct several different property-aware graphs on the corresponding relationships. These relationships of properties extracted from knowledge graph are the most commonly used in real world. For example, director styling and cinematography in the movie field. For each property-aware graph generated, we learn a mapping function FPV2RD by optimizing the object function of node2vector. Through the above steps, an item can be expressed by representation of vectors in all the property-aware graphs as Rj. It is a set. You can see it. In consideration of the real-time requirements in recommendation system, we adopt the LSH mechanism in two different forms termed as local LSH and global LSH respectively. Given a complete sequence LI of items selected by the user UI, calculating the semantic similarity of all items in LI and items in the candidate set will consume a huge amount of time. Note that in these items, many of them have similar properties, so it is feasible to cluster the sequence LI before making prediction. We use the first form of LSH called local LSH to separate all items in LI into different buckets, and items with similar properties will be placed in the same bucket. Since using one single hash function for bucketing is prone to lead discrete accuracy, a group of k hash functions are selected to ensure similar items more likely to fall into the same bucket. Each bucket represents a class of items which are similar in some respects. Thus, we select one item for each bucket as a representative, and then a new performance sequence is obtained by combining representatives in other buckets. Note that in the actual recommendation scenario, items with a higher similarity to the candidate item often have a greater influence on the user's decision. Global LSH is adopted to quickly find the neighbors of the candidate item. Similar to local LSH, global LSH also uses a group of functions to hash the original data. The difference is that in this approach, the candidate item is also hashed. After this operation, items in each bucket can be seen as the most similar items in the global state. Thus, all the items in the bucket where the candidate item is located are selected to form a new preference sequence. Both the sequence generated from local LSH and global LSH can be used to replace the sequence Li for making prediction. The property-aware score SP between Vj in user's history sequence and the candidate item Vc under the property P can be calculated by cosine similarity, and the property-aware scores between the two items in NP numbers of property-aware graphs can be expressed as a SP. We aggregate them to get the final similarity score of the two items Vj and Vc. Scores between each item in sequence and the candidate item can be given as another set Si. Then the final recommended score of the two of Vc for the specific user can be calculated. Part 4 is the experiments. Our model KPG4Rec is evaluated on two real-world datasets. The first dataset we utilized is Mueller's 1 million. It is a widely used benchmark dataset. The type of feedback in Mueller's 1 million is explicit. In this experiment, we take the items rated by users as positive feedback, and these feedbacks are used to construct user item interaction graphs. The second dataset is Last.fm from the online music system Last.fm. In this work, we take two classification accuracy measures, precision and recall, in order to determine the hyperparameters in KPG4Rec. F1 score, which is a comprehensive consideration of precision and recall, is also adopted. In our experiment, hyperparameters in node2 vector are set as follows. Number of works per entity n equals to 50, length of each work L equals to 100. The return parameter P is 1 and the in-out hyperparameter Q is 1. The dimension of vector embedding D is 200. Context size for optimization is 30 and the number of epochs in SGD is 5. Another important hyperparameter is the number K of hash functions. In order to select the appropriate K based on the time consumption and F1 value, KPG4Rec with local LSH is evaluated on the evaluation set of Mueller's 1 million and Last.fm. Precision and fail and recall and fail are used to compute the F1 value. It can be clearly found that as the value of K increases, the model effect and running time are also increasing. Our requirement for selecting K is to minimize the running time while maintaining the original efficiency. For the reason that the F1 value only checks less than 0.02, where the running time is reduced to nearly half. We chose 6 as the number of hash functions in local LSH for Mueller's 1 million. For KPG4Rec with global LSH, we chose 4 as the value of K, similar to Mueller's 1 million. We chose 4 and 1 respectively as the number for the dataset Last.fm. We evaluate our novel model KPG4Rec and compare it against BPR-MF, item KNN, NMF, SLRM, spectral CF top-up. It can be seen from the experimental results significantly that our proposed model performs better than the other measures in both Mueller's 1 million and Last.fm. Part 5 is the conclusion. There are two main contributions in this paper. We propose a novel model KPG4Rec with the enhancement of knowledge graph for top-N recommendation. Extensive experiments have been conducted onto real-world datasets, and the effectiveness of our KPG4Rec framework is validated. For future works, we will apply graph mining methods to our property-aware graphs to better explore users' potential interests, and utilize the recently popular deep networks for a more efficient recommendation. Okay, that's all. Thank you for watching.